So welcome back. So in the last video we talked about the fact that when we deal with covariance, right, between two variables, for example, right, sometimes you get numbers because we might be comparing two different variables with different units of measurements. We might get numbers like say 75, 89. What does that mean? Okay, negative 75 or negative 55 or whatever it is, right? So it's hard to sort of quantify apart from the fact that there is a negative sign versus a positive sign or a zero for covariance, right? That's why we sort of use correlation, which is what basically normalizes. Okay, so what correlation is? Correlation is basically a normalized value of the relationship, that covariance. So you have covariance in the numerator, and it's normalized by the variance of each individual variable, right? So, and it cancels the units out, and hence reduces that measure between -1 and +1. So a correlation of +1 means that the two random variables are perfectly correlated, okay, which you'll seldom find in reality, right? And -1 implies a very strong negative correlation, right? Basically a perfect negative correlation, right? A correlation of 0, of course, means that there exists no discernible relationship between the two variables, and uh, but just like with covariance, so there is a caveat, okay, to that, okay, and we'll get to that now, okay. So covariance and statistical independence, okay. So independent variable is basically when we say that there is no inherent relationship between these two variables, right? So is that really true, right? So we know that the positive and negative covariance terms imply that the calculated variance between the two. But what if the calculated variance? So okay, going back to that. So we know what positive and negative covariance terms imply, right? But what is the covariance between the two? What if the covariance between the two is 0, right? There appears to be no evidence of a relationship, right? So the two variables must be independent, right? Okay. So just because the covariance is 0 doesn't mean that two variables are independent, okay, is what we're trying to prove, right? So let's assume a unit circle, okay. It's just a fancy term of, we know what a circle is, right? And we know we have a radius of a circle. A unit circle is basically a circle with a 1 as radius, right? So that's what we call as a unit circle. And say we define a random variable x is mapped to a value between -1 to +1, right? So it's between -1 to +1, okay? That's the value of random variables in 0.2 increments, right? So y, okay, so let's say x is this, okay, we know the hypotenuse, okay, so when we draw a unit circle, the radius is 1, and we have x and y, right? So we know Pythagoras theorem, right? I'm sure you would have done it a while back, right? And let's take a value for x, okay, we know 1, and let's take a value of x, any value between -1 and +1, right? Because we know it's bounded by these two limits because it's a unit circle, right? Let's take any value for x, right? Because it's the hypotenuse is 1, we should be able to calculate y, right? Okay. So when we do that calculation, okay, which is what we have done here, okay, when we do that calculation, okay, okay, when we do that calculation, okay, before that we do that calculation, so we use x and we use y, okay, y is square root of 1 minus x squared because that's the Pythagoras theorem, right? And we put this 2 in a data frame, okay, in a data frame, in a data set, right? Data frame, we're going to talk about that when we actually start using data in with the Python modules and all, with the Python coursework later on, right? And let's calculate the covariance between x and y, okay? So covariance is 0, okay, because it just so happened that with this kind of a setup, the covariance happens to be 0. So we know that when we actually calculated x, right, when we calculated y, for example, right, from x, we know that x is we know that y is dependent on x. Okay, so that means there is a statistical dependence because we actually used x to calculate y, right? So there is a statistical dependence, but the covariance still happens to be 0, right? Just that's just math, right? Uh, so it's true that if so basically what we are trying to imply is that it's true that if two variables are independent, okay, independent, their covariance is 0, but the reverse is not true. Okay, just because we find out that the covariance is 0 doesn't mean that the two variables are statistically independent, right? So if the two variables is 0, then they can still be dependent, is what we're trying to find out. And that's because covariance, and hence correlation, because covariance is normalized, correlation is normalized covariance. So covariance is basically a measure of linear dependence. Okay, it doesn't, and so here it's a non-linear relationship. Non-linear means the slope is changing as you change the variable, the value of variable x. The y is acquiring not a linear line. Okay, it actually has a changing slope. It doesn't have just one slope, right? So it has multiple slopes. So the slope is changing. So it's a non-linear relationship. So that's very important to sort of realize as to what linear relationship is versus non-linear relationship. Okay, linear is basically you have sorry, I'm pretty bad at drawing, as you can see. Okay, you have x and y. Okay, x, y. Okay, and this is your linear. Okay, so this is basically as x goes up, as x increases, the y increases. Okay, or it could be like this. Okay, as x increases, y decreases. Okay, so that's linear. Okay, okay. Non-linear would be something like this. Okay, this is non-linear. Okay, that means x initially, as x increases, y increases initially, but then it drops again and then it goes up again. So that's a lot of the time it's reality. And when we get to that section where we deal with predictive modeling, we're going to start looking at as to what we do, what we need to do with this non-linearity in your data, right? But so what it is telling you is just because they are the covariance is 0 doesn't mean that they are not dependent. Okay, there could be still statistical dependence. Okay, okay. So along the same lines, if correlation is 0, okay, correlation is say rho xy, we can say that x and y are uncorrelated, and if the two variables are independent, okay, their correlation will be 0. However, just like with covariance, right, it doesn't go the other way, right? A correlation of 0 does not imply statistical independence, right? So now that read through this. Okay, this should be pretty evident in terms of what we are trying to say here, or what I'm trying to say here, right? And this basically is just a definition of what it means to sort of say that these two variables are correlated, right? Okay. So going back to the two time periods we were looking at, right, where we manually calculated the covariance between interest rates and the stock market, right? This is we did it manually before, but now we are using this co function. Okay, so this is and in Python. Okay, by the way, I'm using R as a tool. Okay, you're going to be using Python. Okay, it's the same exact. It's a little bit of a different programming language, right? The fact that I wrote it in R, I'm just explaining it in R. But when we actually use some of the later on in the lectures, you'll be mostly using Python, and you're glad to explore R. Okay, whenever you get a chance, right? It's another statistical programming language. Okay, so you can actually directly calculate covariance, right? So as you can see, between interest rates and the value of your portfolio, you have the diagonals are basically the variance terms, and the off diagonal are the covariance term, right? So of course, the off diagonal, which is -37, it's almost the same on both cases. It has to be exactly the same, right? Because the covariance between interest rates and in the value of your portfolio doesn't change, right? Depending upon where you put it on that diagonal. And similarly, so this was with one time period. This is the another time period, right? Now, the diagonal elements of the covariance above are the variances, and the off diagonals are covariance. We already talked about that. You might have noticed a small difference, okay, with 8.87 is the value here, okay, for the covariance. And I think if you recall, we calculated the covariance to be 7.76, okay. And so that is the difference, because we are dealing with sample, okay. We are assuming this is population data, okay. What the tool uses is sample data, okay, and there is a little bit of a difference in how the sample versus population math is to calculate standard deviations, variance, and covariance, and all those things, okay. And we are going to explore that, okay. But all I'm trying to say here is that that's due to the fact that most tools calculate sample statistics and not population statistics, and the difference between the two has to do with degrees of freedoms, and I'm going to explain that concept. Okay, by that just to sort of elaborate on that. Okay, here I'm already listing it out. By that we mean the number of values in the calculation of the final statistics that are free to vary. Okay, don't put a lot of thought into it. If you all you have to take away from here is that anytime you're dealing with an Excel or R or Python or whenever you're calculating covariance, almost all the time they will be calculating sample covariance and sample variance instead of population variance, right? And there is a little bit of adjustment you have to do, okay. So that gap in value between sample and population statistics reduces as sample size increases, okay. And that's pretty conceptually is pretty evident, right? The larger the sample size you're going to take, the more it is going to represent the population, right? And that's what you're trying to measure, right? You're trying to measure what's going on in the population by picking a sample which is easy to do, which is cheap to do, right? It doesn't take a lot of effort to collect a sample of data as opposed to measuring everyone's height in this. The difference between that is, let's say someone says, okay, what's the average height of everyone in this country, okay, and what is the standard deviation, okay. Everyone in this country is everyone in the United States, right? Let's say, for example, you're not going to be measuring everyone, right? You're going to take a sample from different parts of this country, and you're going to get a few samples together, and you're going to combine the data and sort of get those statistics, right? So that's what sample versus population, and the bigger the sample size you take, the better of an estimate of the population parameters you're going to get. Okay, a little bit of a sidetrack. We are going to talk about sample. I know I keep talking about all the things we are going to talk about, but we are actually going to talk about that. Okay, hopefully. Okay, so now that we have the requisite background, okay, of what correlation, covariance, and all those terms are, right? Let's go back to our asset class return data. Okay, we still want to go back to that thing, okay, and let's look at the correlation matrix for that entire time frame. Okay, I think we started off with 1970 to 2018, right? So we have asset class returns data, and we know what asset classes are, and of course this is a correlation. Okay, correlation, when you look at the diagonal elements, they are always going to be 1 in a correlation matrix, because we are looking at a correlation matrix. Okay, diagonal elements are always going to be 1. The off diagonals are basically the correlation between these two variables, right? Correlation with itself, the variable large cap US equity to larger US equity is of course going to be 1, right? And it doesn't add any value. Okay, but between large US equity and small company stock, it's pretty high correlated. It's positive, right? Of course it makes sense, right? If the economy is in a bad shape, right, not only are the large companies going to suffer, but even the small companies are going to suffer, right? Same thing between large company large US stock and an international stock. makes sense, right? Global economy, if US is not doing right, then the rest of the world is also. I think there is a saying that when US gets a cold, no, when US gets a something like that. Okay, when US falls sick, the uh, the rest of the world gets cold or something like that, so something like that, there is a very strong relationship between what happens in US versus what happens in the rest of the world, economically as well as from the stock market perspective, right? And you start getting into different types of investments where you see that bonds are not as correlated. Cash and the stock market is pretty almost no correlation, right? Zero correlation. And then you get into commodities, which is a slightly negative correlation, right? Okay. So that all makes sense, okay, and this is what you would typically do. You'll get into a data set, right, and you'll have multiple columns, and you'll the first thing or the first few things you'll do is you sort of get a gauge of what variables are related to what, right, and why, right. So you will sort of have to sort of reason it out, just like I'm reasoning it out here, as to why do I think large US stocks are correlating very well with you small company stocks versus international stocks, right? So let's look at a time frame before 2000, okay, and let's look at two different sets of correlation metrics, before 2000 and after 2000, right? And you see some differences. So before 2000, right, you see that between the US and international, okay, US large cap, US small cap were sort of correlated pretty reasonably well, but the internationals were not. But after 2000, the international, the correlation actually went up. Okay, again makes sense. Okay, and the reason is that I guess the world became more and more global. So one argument is, okay, so this is, see again. So I'm trying to sort of fit my understanding of what is going on in the data with what I see in the world, right? And that's what you would typically have to do in your world if you're dealing with data. That you're going to be exploring data, okay, and you're going to fit a theory which has to sort of make sense, of course, because if you end up fitting the wrong theory, you're going to end up making wrong conclusions and you're going to end up making wrong decisions, right? So you don't want that to happen too much, okay? And it sort of makes sense, right? Because the world has become more interconnected, more globalized, and whatever happens in the US happens in the rest of the world as well, right? And let's see what else we're going to talk about, okay, and look at that change, okay, so and we can sort of visualize. So if you don't like, I like to look at the numbers like this, but maybe if you want to get a little bit more fancy, you can sort of look at it in a plot form, and it looks same information in a plot form, right? And your the diagonal elements and the off diagonal elements, right? And you're looking at these different time frames before 2000 and after 2000, right? And okay, one interesting plot here, okay, and then we're going to get into the rest of the stuff, okay. So this is XLF, okay, again dealing with financial data again, right? uh, it's very easy to sort of explain some of these concepts when you're actually dealing with something which you can relate to, at least with the data set we're dealing with, right? So XLF is a financial sector ETF. That means it has all financial type banks, investment banking companies, mortgage companies, and so on. So it's a collection of companies in this one stock. So if you wanted to say, go out and say, you know what, I want to get exposure to only the financial sector in this country, okay, you would go out and look for something called XLF. And when you open XLF, when you look at XLF, you're going to have let's see that, okay, just to make sure that you get a flavor of what XLF is, okay. Okay, XLF. Okay, I've never been to this site before, but I assume it has information we need. It's called ETF. Okay, by the way, this is an exchange traded fund. Come on. Okay. Okay. It's showing up. Okay, XLF. Okay. And let's look at what it has. Okay, it says financial sector, select ETF. and it has a bunch of information. Okay, and what I'm trying to sort of look for is what does it own. Okay, so if you can see, this is either my internet is a problem or this site is a problem. Okay, and come on. Okay, what I wanted to see, it's a pretty bad site. It's loading a lot of data. Okay, so as you can see, it has exposure to banking services, investment banking, insurance business, and professional commercial. Okay, and these are all the companies which are part of that. Okay, so there are top 10 holdings. Okay, Berkshire Hathaway, J.P. Morgan Chase, and come on. Okay. Still loading. I cannot believe it. Okay. I wanted to show, not to spend too much time. Okay, by the way, so this is all United States companies because it's all companies here locally. Okay, in this country. Okay, so while this opens up, okay, let it open up. Okay, and what we are doing here is if you look at the correlation between XLF and JP Morgan Chase, which is a big bank, you see pretty high correlation. But in some point, because it's one company versus a basket of companies, right? Sometimes the correlation goes crazy because maybe JP Morgan basically suffered through a bad quarter, right? And the stock drops, but the rest of the companies are still doing fine. Okay, so that and sometimes the correlation is close to 1, sometimes it drops below 0.5, and so, right? So this is one way to look at correlation. And what that also tells you is that sometimes you can deviate from what the inherent sector is doing, right? So that's the risk of investing in one company, right? Sometimes you are doing very good, sometimes you can do pretty bad, right? And let's go back to that just to make sure it has opened up. Okay, and it has a lot of data. It's a pretty neat graphics, a lot of them. Okay, and it has a lot of information on this page. Okay, it's done pretty badly, and you know what is going on nowadays. We have this coronavirus thing, right? And look at the top 10 holdings, right? So you have Berkshire Hathaway, JP Morgan, Bank of America, Wells Fargo, Citigroup. I assume this is Chicago Mercantile Exchange, American Express, BlackRock, Goldman Sachs, and so, right? And you can look at all the holdings. It probably has a couple of hundred holdings, or at least 100 holdings. Okay, I'm not quite sure what the exact size is. Okay, so that's a little bit of correlation, statistical significance, and the rest of the good stuff. Okay, we'll move on.